Yes, now we discussed about this 1 comma n like shift so in that we were concentrating on hydrogen as well as carbon, and we worked out some examples based on that. Now we will take another part of your sigmatropic reaction, that is your n comma m sigmatropic rearrangement. Fine. So, what is that n comma m is a system like this. I am numbering here 1, 2, 3, 1, 2, 3. The sigma bond initially is 1, 1. Okay. So, it is 1, 1 position sigma bond. So, after the reaction, where it has moved 3 3. So, this is your n and this is your m. So, then it becomes 3 3 sigmatropic shift. Fine. So, in n comma m sigmatropic shift, we are going to concentrate mainly on two. One is like your 2 comma 3 sigmatropic shift and your 3 comma 3 sigmatropic shift. Yeah, we will see some few examples on 5 comma 5 and 9 comma 9, but 2 comma 3 and 3 comma 3 we are going to cover more. So, what you studied in 3 comma 3? 3 comma 3 you have lot of reactions, right? What are they? Cope, Claisen. Claisen may you have lot of modification of Claisens are there. Then in sigmatropic 2 comma 3 you have your any reactions, Wittig, Stevens, Somel-Tazer, right. So, all these reactions we will cover. Fine. So, we will start with 2 comma 3 sigmatropic shift. That what we are going to see. First, we are going to see your Wittig reaction. Initially, we will cover all the reactions, okay, then we will do the problems. Okay. Any idea what is Wittig reaction? Studied about idea of the substrate at least. What substrate we deal with Wittig reactions for this 2 comma 3? Allyl ethers. It works nicely with your allyl ethers. So, you can take a type of allyl ether. Okay. No, you are talking about that allied chemistry. No, it's sort of Wittig rearrangement. Okay. Okay. Much more to be clear, I will say it is Wittig rearrangement. Otherwise, it will confuse with your reactions. Yeah, that is good. So, if I put butyl lithium, so I can generate an carbon anion, right. Yes. Now what happens if I heat this guy? What you can observe if I heat this? Can I number this? 1, 2, 1, 2, 3. Fine. So, you have a key. See, if I am doing this in lithium, you get like O minus Li plus, that is always there. Right. So, now where the new bond is formed? Your new bond is formed between 2 and 3, right. So, the second and third position. So, that is why you call this as 2, 3 Sigmatropic reaction. Sigmatropic reaction or Sigmatropic rearrangement. Because this is where, because I ask people like 2, 3 write an example, no one writes 3, 3. You just know where the N and M gets the formation of the new sigma bond, and this is the best example for your Wittig. You have this Stevens rearrangement. Stevens rearrangement is similar like your Wittig one. Wittig, you take type of allylic ether, right, which is an oxygen. In Stevens, you talk with nitrogen, that is all. Guys, you should know all these reactions. At least someone asks, you should be able to know this. Again, I can use my beta lithium. Generate an carbon anion. And this on heating. What it can you so now you can easily number this, right? I missed my. So it is 1, 2, 1, 2, 3. So you have to form a new bond here, right? Yes. Good reactions. This is your Stevens. First you saw Wittig rearrangement, now Stevens rearrangement. Keep this all in mind, because when you do problem you have to see this, guys. Whenever you have an allylic system, okay, to an heteroatom, please think about this type of rearrangement. Allylic system to an heteroatom. Then you can talk about your Somlat. This at least you should remember, na? So, SSER, double S, okay, Somlat Asser rearrangement. HAUSSER. What is that? Studied Somlat Asser. Again it is 2, 3. Oh, sorry. Take a type of quaternary salt, and now it's we can create a anion. Create an anion here. Fine. Now can you number it? It's again 2 comma 3, right? 2 comma 3 sigmatropic shift. So its positive is always there. 1, 2, 1, 2, 3. Okay. Get this compound, then which can get back to aromatization. Famous reaction, Somla-Tasser. I know that you have studied this type of rearrangement, just it's better that you refresh them back again. But it comes under a class of 2 comma 3 sigmatropic. There you would have studied under rearrangements. Okay. Here it comes at a nice of 2 comma 3 sigmatropic. And another is your Mason-Himmer study this, right? Remember at least Mason-Himmer rearrangement. What is that? Mason-Himmer rearrangement. It's again it's an allylic one. But in this case you take with your N oxides. N oxide, even you can do with your S oxides. Okay. If you eat this, number it 1, 2, 1, 2, 3. Right. Two comma 3. Even same reactions you can try with your sulfur. This also you can try with your sulfur. So, this is your misnomer rearrangement. So, you have studied 4 types of rearrangement in 2 comma 3. At least if someone asks 2 comma 3 rearrangement, you should tell at least one out of it. So, your Wittig, Stevens, Somla-Tasser, then your misnomer. These are a well like very common 2 comma 3 sigmatropic rearrangements. Okay. Fine. So, that's more about 2 comma 3 important rearrangements of 2 comma 3. Now, we will slowly get into your 3 comma 3 sigmatropic. There you have studied a lot, 3 comma 3. So, your famous one is your COPE. So, cope you are not forgot, right? So, 1, 2, 3, 1, 2, 3. That's your 3, 3 sigmatropic shift. Okay. Now, if someone asks you this cope rearrangement goes like free radical, if someone argues that it goes by free radical, it does not go by your transition state chemistry, any idea how you can say that argument is wrong? If I say this reaction goes only by free radical mechanism, cope rearrangement, it breaks here, I get a radical. You want to say no to that. Can you say? How you can say that?
If there is any asymmetric center or is asymmetric, some reciprocation.
You can get that. Another thing, can I deuterate this? For example, I can deuterate here 2 deuteriums. Okay. For example, I am taking this compound. Okay. So, 4 times deuterium. If it cleaves here, then you end up with a radical, okay, and I will end up with a radical here. Okay. This can directly connect, that is 1-1 combination, or this can do a 3-3 combination, but this can also do 1-3 combination, right, other way around. So, that you cannot find it out. Okay. That is one good example saying that this chemistry does not work by free radical. Okay. Another important thing, you can say that the kilocalories for cope rearrangement is just 35 kilocalories per mole. Okay. If you want to break a CC bond, how much you need? Homolytic cleavage of your CC bond, 85 kilocalories per mole, but this is far less. Okay. So, this reaction does not go by free radical, it goes properly by your transition state. Fine. And if someone wants to argue, okay, you can just argue like that. Okay, in why this cope rearrangement goes sort of suprafacial or anterofacial? Cope rearrangement. Yeah, it moves more like a suprafacial. So, what happens is that if I just take the retro of this, it should form a 2 allylic. If I think it forms an allylic type of bond breaks, it forms type of allylic radical, if I can. So, shall I write the, and then it gives me my product. So, how I write the HOMO and HOMO of this guys, because we know that to write the HOMO of this, that is how we studied this. Okay. And the other face of it, see, it is orbitally well favored. Okay. Just it has to combine, nothing it has to do. Right. So, that is, it does not need to do any inversion or anything, just it has to combine. So, that is why suprafacially it does, orbitally it is well favored and the reaction goes so nice. Okay. This is your cope. Okay. The interesting part of cope rearrangement comes when you talk about the stereochemistry. Yeah. or not r prime, just keep it r itself, both are r. Okay. Now, tell me, if I do a Cope rearrangement, what are the products I can think of? Now, I have two substituents, I kept two substituents. What are the products I can think of if I do a Cope? You get only one product, are you sure? Just asking, possible. You do not get only one product, you get two, but possibly how much you can think of? Just two. Yeah, you can think of. See, in one case I can have my R, right, I can get this. So, what it should be? E and E, right. I can think about then where R inside and H, right, Z and Z, right, your R inside. No? Another case I can think about R outside and your one R inside. So, it can be Z and E, right. So, and E and Z both are same, okay, E and Z and Z. So, you can think about three products here. No, it is not only one product, you can think about three products when you talk about the Cope stereochemistry. You can get E and E, you can get ZZ, you can get Z and E. So, any idea which will be more? Which will be the major product, not more, major product? E, then ZE, are you sure? What happens, yeah, how to figure out this, which will be major, okay. It is an easy way to figure out. Just I will take this compound, okay. I have two methyls, fine. It's one, it can be, I can write like this, right, where your two methyls can be equatorial. I kept two methyls as a equatorial, fine. It can exist in other way also. What are the other way? Where two can be axial, right, two methyls can be axial. Shall I draw that? So, two can be axial. Another I can think about is what? It can be in a boat form also. No? You have studied for your cyclohexane. See, this three way I can write your structures, right. So, if I write the transition state for this, for example, can you write the transition state, anyone? What transition state can you look for this? Because the bond has to move, clear up this. So, you get a nice 6 membered see, this is the beauty of Cope. Can write for this. This also I can write a nice 6 membered, transition state, I can also write for this, but this will be more like a boat. Okay. So, if you write the product for this one, your methyls will be outside, right? This will be E and E. Right, for this, that should be Z and Z. That should be E and Z. See, you can write 3 nice way. Okay. Yeah, at least you can see this is chair and this is boat and you have a chair. Okay. Now, the first question we can ask, because we studied about cyclohexane systems a lot, right? Which is chair is stable conformer or boat? Chair. Okay. So, that means this is gone. Okay. So, cope will now this reaction you have less than 1% you can get this product, because it goes through boat. So, it is unfavored. So, you get your EZ or ZE very less, not you, very less, okay, less than 1%. So, you are not. So, now you say that I have now both chair, right. In both chair, which will be much more stable. The system which you have studied in cyclohexane, the methyl should be where? It should be equatorial. So, in this case they are equatorial, right. So, you get 90% of this product and then you get 10% of this. This is very less, okay. That is why it is. Now, you understand how you have to see the stereochemistry of your cope. Okay. Just take that, write it in a chair form as well as in the boat form, then think which should be equatorial and which should be axial and which is boat form, and based on that you can predict which will be your major compound. Any doubt with this stereochemistry? Okay, that is good. Now, we will just see this rate of interconversion of your cope. I have this one, okay. I have taken this, I do a 3,3, you know that what product you get. See, the energy barrier for this reaction is 34 kilocalories per mole, okay. So, it takes interconversion. So, this can be pretty well isolated, yeah? Fine. If I want to increase this rate, I want to increase this rate of interconversion, I want to make this interconversion very fast, what I have to do? Any idea from your side, any suggestion? I want to make this energy barrier less and I want to interconvert this very fast. You can have substitution in 3 position. Any other? Yeah, good suggestion, no problem, because you can do your oxycope, na? That comes under that category. Yeah, another. See, there is one way of doing it. You take the same system, just have a strained ring on the surface, na? Just keep your cyclopropane very strained, because then this bond will break fast, because it is under strain, so it breaks fast, very fast. Okay. Then you get and if you see the energy barrier, it is 9 kilocalories per mole, even hard to isolate, just they interconvert very fast. Okay. Still want to make it faster. What is that big cope you have studied which does very fast? You have studied that? Yeah, I will make other side also strain, like taking a big molecule like. What is this? Name of this compound? Homotroplidine, right? Homotroplidine. Yeah, I will make caps. So this does very fast cope. The interconversion is very high. So one more molecule you studied under cope which gives you millions of tatameric forms. What is that? Just gives you million of tatameric. It just interconverts so rapidly. You can write million tatameric form for that, and a very famous compound. It comes under a category of flexinol. Same extension is extension. Can you remember? I will just draw the structure, at least if you can say. You can even draw cope for that, very famous cope. What is this? I have studied cope on this. Bulwelline. Right? It undergoes sort of cope very fast and rapid, bulwelline, and this falls under a compound called flexinol. You call these categories flexinol categories. I think you can write like million tartameric form of this compound, bulwellins. Very famous thing. So in cope, yeah, that's how you can increase the rate of your cope interconversion. You can put your ring strains here and there, and you can do your, and they fall under flexinol categories. Okay, that's fine. Yeah, I said like in examples we'll see all the reactions later. First we will cover the reactions. Then the important modification of cope is your oxycope. Yeah, oxycope one is that if you take this simple alcohol, right, you can do a heating, it undergoes a 3,3. So 1, 2, 3. Get an enol form, which can't atomerize, which atomerises to give you a kit, right. This is your oxycope. Any importance of oxycope? Oxycope becomes very famous in one sense. If I remove this hydrogen, make an anion O minus, okay, then what happens? Because you can take an alcohol, yeah, it does to enol and gets you the ketone, yeah, reaction goes. But if I remove this hydrogen, make it O minus, what do you expect? Oxycope. People do that. That's how oxycope becomes, like you become lithium salt or you make O minus Li anion. See, oxycope reaction goes very fast, okay, if you make an anion, because what happens that the oxygen anion stabilizes your transition state, okay, where the charge get dispersed and your transition state gets the energy of your transition gets lower compared to your regular cope, okay, and the rate of the reaction is very fast. So, if you just enolate this, like you make O minus, you end up with a very fast reaction, okay, that is very beauty of oxycope, fine. Okay. The another variation is azacope rearrangement, that is also there. So, I have 1, 2, 3, you can write 1, 2, 3, heating 3, 3. Your azacope. Okay, it's clear. This is about cope. Now we will take one interesting fact of this type of rearrangement which I have studied, and ask ourselves some interesting things. See, when you it has been in many papers, okay, when you take this onion, right, and you chop this onion, you get like tears from your eyes, right. Why have you any thought about it, why it happens? Onion and as well as garlic, may you get a very odor smell, right. Have you seen the chemistry? Lot of pericyclic reaction is involved in that, why you get this tears from your eyes, and there you can see lot of sigmatropic reactions and cope rearrangement all happenings, okay. We will just take that example, we will see how it is, why it happens, interesting one. See, if you take an ordinary onion and you chop it, see, in onion you get this compound O minus S plus. Okay, you have this. When you chop the onion, this whole thing happens. There is an enzyme called alinase. Okay, this just cleaves this bond, fine, to give you get this. And what beauty of sulfur? What sulfur does? It undergoes dimerization very fast, nah, that you are saying. So, it can dimerize, then just when you chop this happens, not the other time. Okay. You take onion, once you start chopping it, you get this molecule which is allinase, and then it dimerizes.
So from where this allinase come?
In the onion. Yeah, it is an enzyme. O minus, you get S plus. Sort of dimerization happens because that is known in sulfur chemistry. Then in air, just in air, this guy becomes sulfonate. Okay. So, this sulfonate which you get, this is the guy which is responsible for that raw smell of onion. Because of this only you get that raw smell, onion smell, this sulfonate. Now, what happens if you chop this particular compound? Okay. SOH, what it can do? Think of any pericyclic reaction, what it can do. If I write like this, you will not think. Shall I write in other way? Very good. It undergoes a 2,3 sigmatropic shift. So, you have an O, you can have an hydrogen here. Okay. Undergoes a 2,3 hydrogen shift. So, you get this, right. Then you can, oh sorry, it should be other way around. Your anion should, that means I have to break my bond this way across this, and I have to break O minus. Okay. So, it should be my hydrogen, yes, O minus and my plus, it should be like this, fine. So, this arrow is this way. So, you have your 1 3 then. So, this is the guy which is your lachymeter, okay. Lachymetry, which gives you TS. Okay. This hydrolyzes by your and end up with your aldehyde. Okay. This is the reason why you get TS. Okay. This is a compound. You call this as a very good, because there are many lachymeters, right, and this is one of the sulfur compounds. Very good lachymeter. Jara, if you take little bit, keep it in eye, you will start crying. Okay. This comes from your onion. So, once you chop onion, this does. And you have studied this, see, that's in onion I said this compound, right, we were talking about this compound, that is why it is you get, because this undergoes lot of 2,3 sigmatropic shift, giving you this lachymeter compounds, and you get here. This is another interesting compound, this part and this one. This is also interesting compound. Why? Any idea this particular compound? Because you end up with a very nice compound which is used for your heart disease, anti-cancer, because eating onion helps you out to get out from your anti-cancer, heart disease, garlic pura. It is very good for your thing, anti-cancer, and that is because the sulfonate which we are talking about. See, onion and garlic are very good. I have this compound. Think about anything. What pericyclic reaction it can do? What pericyclic reaction you can think about? Unless very good, you can do your nice scope. Alright, 1 2 3 1 2 3, you can do your cope rearrangement. Yeah. Oh, sorry, I have in this case I have, because it is a dimerization, we have missed a methyl there. Methyl is missing. Yeah. So, if you do you can do 3 comma 3, very good cope rearrangement. Okay. So, you end up with what product? This methyl here, methyl here. This is called as sulfine. Okay, and sulfine undergoes, which you are not studied, yeah, even you are studied in a photochemistry, it undergoes very nice 2+2 cycloaddition. Okay, this sulfine undergoes a 2+2 cycloaddition to give you your famous drug molecule. This you call as Zubeling. This is a guy which is recent for your as a drug for heart disease, antifungal. You know that garlic and onion, very good antifungal property they have. This is because of this Zubeling, and these are all proper pericyclic reaction, right? Your lacometry is because of your 2,3 sigmatropic shift, and this your Zubeling comes from your type of cope rearrangement. So, you can remember at least when you take about your onion and garlic, you can think about your pericyclic reactions, right. So, there are many examples, I will just come with examples lot. Just I want to show that yes, they have like some sort of things to be remembered. They have very good applications in normal things. Okay. So, that is about your cope. So, what I will be doing, we will be starting problems including all these things 1 comma n and n comma m, and then we will do all the problems. That time we should know whether we are going to do 2 comma 3 sigmatropic or we are going to do 3 comma 3 sigmatropic, all these things. Okay. Another I will start giving introduction. Another important reaction in 3 comma 3 is your after cope Claisen. So, Claisen is similar like your cope, just you will have an oxygen in the system, right. So, then I can make 1 2 3 1 2 3. So, it can be 3 comma 3 sigmatropic shift, giving me an here 3 comma 3 Sigmatropic shift. Claisen. Any idea how to make this compound? There are many methods to make, just the precursor, anything the old methods which you have studied. Yeah, there are now a lot of methods to make this allyl type of ethers. If I give this compound, I ask you to make this one, how you make? Which method? Wilkinson. Any other good methods? You can take your, see if you take your simple, just try this mechanism. I will just give this method. See whether you can make, it's not pericyclic, but just for curiosity, can you write this? If I take this compound, okay, with my allylic alcohol, I get my precursor for my Claisen. Take this, take an type of ketal, take my allyl alcohol, react, I get this. Okay. Then if you heat, you know that it undergoes a Claisen rearrangement to give me the product. Just try this mechanism and get to this product. It's an interesting mechanism. Just try that. Okay. So next class we will again get on Claisen and the different variants of Claisen rearrangement. Fine. So with this we will end our class today. Thanks.